Hello, and welcome back to the course, Physics 123, Quantum Mechanics 1. We are now on our third lesson for Chapter 1. So before we start with today's lesson, let us first review some of the concepts that we have learned in the previous lessons. So we have discussed on on how to find the probability of discrete and continuous variables, and also how to calculate their expectation values, or also what we call the mean or average values. We also have discussed about the standard deviation, which just defines the uncertainty of your uh, data. And lastly, uh, we have an example where we show you how to sketch the probability distributions, how the shape look like, and what is the area under the curve of a probability density function, which is just the probability essentially. For today's lesson, we will now relate those discussions to our wave function. So we have encountered about the normalization condition in the previous lesson, and we will now try to relate the normalization of the probability density to our wave function. So in our first lesson, we define the wave function as related to the probability uh, that, say in this case, if your continuous variable is x, the probability that x lies between a and b. So this is the statistical interpretation of the wave function. So of course, if you integrate over all possible values of x, say from negative infinity to positive infinity, you should get a total probability of 1. So meaning there's a 100% chance that you will get a value of x. So in our previous lesson, we termed this expression as the normalization condition, where the integrand there was our probability density rho of x. So in this equation, the role of the probability density falls to the absolute value of our wave function squared, absolute value of psi squared. So that's actually the probability density, rather probability per unit measure, probability per unit position, or probability per unit momentum, or probability per unit energy. So if you have this type of probability density distribution, when I say probability density distribution, it's a distribution or the plot of absolute value of psi squared, which is just equal to rho, our probability density. Then this means that the total area under the curve of your probability density function must be equal to 1. So it represents the total probability, which is 100%. So based on this condition, it is found out that only square integrable wave functions are the acceptable solutions to the Schrödinger equation. And these square integrable wave functions belong to a space called the Hilbert space. When you say square integrable wave functions, it means that if you square the wave function and you integrate it, you must get a defined value. You must not get an undefined value. So if your wave function satisfies this equation and it has a defined value, then it is a square integrable wave function. So note that in the normalization condition, the absolute value of psi squared is generally the conjugate of your function times psi. So take note, this is a complex conjugation operation. So if you have an imaginary component of your function, then the I becomes negative I. But if you have real wave function, then this absolute value of psi squared is just psi squared for real wave function. For complex, because our wave function here is in general a complex function, so for complex function you need to take the conjugate multiplied by itself. So the Schrödinger equation actually preserves the normalization of your wave function. So meaning, uh, if you take the time derivative of this integral, then you should get 0, meaning the normalization is time independent. It doesn't depend on time. So if you normalize the wave function at a certain time, it becomes normalized at future or at a later time. So for instance, if you have a wave function like this is the shape of your probability density distribution, absolute value of psi squared at time is equal to 0, initial wave function. So you normalize it, so the total area under the curve is now 1, meaning 100% probability. At a later time, the shape of the wave function may change, therefore the shape of the probability density will also, which is absolute value of psi squared, may also change. But the total area under the curve, the integral of the absolute value of psi squared dx must be always equal to 1, which means at a later time, the maximum probability is still 100%, which should be the case, because there's no probability is always, the maximum probability should always be 100% all of the time. That's the maximum. There's no less than 100% or above 100% maximum probability. So the total probability is time independent. It doesn't depend on time. It's always equal to 1. The total probability is always equal to 1. So let's have an example. Okay. So we are given the wave function of a particle, and at time is equal to 0. So meaning this is the initial wave function. At time is equal to 0. At time is equal to 0, this is the wave function of the particle. So there are 3 regions here. From 0 to A, the wave function is like this. From A to B, the wave function is like this. And otherwise, meaning beyond B and beyond 0, the wave function is 0. Okay. So you are then asked to normalize the wave function. When you are asked to normalize the wave function, it means that you have to find the normalization constant. In this case, the normalization constant is A, this one. So sketch the initial wave function as a function of x, of course at time is equal to 0. And where is the particle most likely to be found? And what's the probability of finding the particle to the left of A? And you are to check your results for the limiting cases B is equal to A and B is equal to 2A. And lastly, what is the expectation value of x, or the average value of x? Okay. So for the first problem, you are to normalize the wave function. So we will use the normalization condition. Sorry. Okay. So we will use the normalization condition. I'm just gonna review our wave function. So this is our wave function. So if we want to normalize this wave function, then the integral over all space of our wave function squared, in this case initial wave function, must be equal to 1. Okay. The limit here is from negative infinity to positive infinity. So actually we have how many intervals here? We have 1, 2, 3, 4 intervals. So you have this integral from negative infinity to positive infinity is actually 4 integrals. So you have from negative infinity to 0. What's the value of your psi squared there? Plus from 0 to this one, 0 to A, absolute value of psi squared dx, plus from A to B, absolute value of psi squared dx, plus from b to positive infinity. So absolute value of psi squared dx. So this should be equal to 1. Okay. So take note that only the intervals 0 to a and a to b has a non-zero wave function. So from negative infinity to 0, the wave function psi is 0, therefore the integral is 0. From b to positive infinity, the wave function is also 0, therefore the integral is also 0. So we only need to evaluate these two integrals here from 0 to a. So from 0 to a, our wave function is this one. So you will notice our wave functions are real. There's no imaginary, there's no I here, there's no imaginary components. So the absolute value of psi squared is just psi squared, the square of your wave function. So the square of this is a squared x squared over a squared. So for this term here. So we have, I will take out the constants. So positive a is a constant, big A is a constant, small a is a constant. So naka-square, square. And then the only thing inside the integral is x. So x squared dx from 0 to a. For letter B, so this is our wave function. So you square that one. Since just real, no need to take the complex conjugate and multiply it by itself. So the constants here are a squared over b minus a squared. And inside the integral from a to b will just be b minus x squared. So this one, b minus x squared. So that would be b squared minus 2bx plus x squared dx. And that should be equal to 1. Okay. So I will leave the rest of the solution to you because these are just elementary integrals. Integral of x squared is just x cubed over 3. Integral of x is just x squared over 2, and so on. So I will just leave the rest of the solution to you. So you will get a value of a, your normalization constant, a value of square root of 3 over b. And your wave function will now look like, initial wave function will now look like this. You just replace a by square root of 3 over b. Square root of 3 over b. Okay. So that's for the first problem. For the second problem, sketch the wave function as a function of x. So, okay. So we have 4 regions from negative infinity to 0, in which the wave function is 0, so flat lang, line. And from b to positive infinity, the wave function is also 0, so flat lang, flat line. Okay. From 0 to a. So, what type of function is this? This is a linear function. So, it's a line. So, from 0 to a. So, at x is equal to a. So, when x is equal to a, the value of the wave function is, so a over a, 1. So, square root of 3 over b. At x is equal to a, the value of the wave function is square root of 3 over b. And at x is equal to 0, the wave function is 0. So, it's continuous, 0. So, it's a line. Just connecting those 2 points. And then from a to b, so here similarly when x is equal to a, so b minus a over b minus a, so it's still square root of 3 over b, your normalization constant. And then at point b, when x is equal to b, b minus b, you have 0, so 0. So it's a continuous here. There's no discontinuity. So it's a line. It's a line sloping downwards because it's negative x. Here it's positive x, so it's line sloping upwards. So this is your plot of your initial wave function. So it's a line, it's triangular. Okay. So for letter C, where is the particle most likely to be found? So actually, from the previous sketch, from this sketch here, since the most probable value is the value with the highest probability density, highest value of absolute value of psi squared, And if you have the highest value of psi squared, sometimes it relates to uh, the maximum value of psi squared also correspond to the maximum value of psi. So in this case, it's x is equal to a. But for formality reasons, the solution to this equation is actually to plot the probability density function. Take note, this sketch here is not a probability density sketch. This is still the wave function sketch. If we take the probability density sketch, we need to square to take the absolute value of psi squared. So we square our wave function. So from 0 to a, it becomes now 3 over b x squared over a squared, and so on. And the plot of this function will look like this. So from 0, so 0 again from negative infinity to 0, 0 again from b to positive infinity. But from 0 to a, x squared, it's a quadratic equation. So it's a parabola. So it's a parabolic. So this one is a parabola. And from a to b, it's also a parabola. It's quadratic. So x squared. So like this. So this is now the plot of the probability density distribution or probability density function, absolute value of psi squared. So you will notice that the value of x with the highest probability, which is probability density, which is 3 over b, is found at x is equal to a. Finally confirming our initial suspicion that x is equal to a is the most probable position of our particle. Okay. So for letter D, you are asked to find the probability of finding the particle to the left of A, and check your results for these two limiting cases, B is equal to A and B is equal to 2A. So let's go back to our probability density sketch. So this is our sketch. So we need to find the probability that the particle or the value of x is to the left of A. So meaning if this is A, to the left of A, so this side here to the left of A. So meaning we only need to find the area under these curves, because the area under this curve from 0 to A represents the probability of finding the particle to the left of A. So our formula will be like this. So we integrate from negative infinity to A, because that is the meaning of to the left of A. But actually, from negative infinity to 0, the wave function there is 0. So this integral, the contributing term in this integral is only from 0 to A. Okay. So from 0 to A, so we integrate our wave function only from 0 to A. So the probability of finding the particle to the left of A is just the integral from 0 to A of our wave function squared. So it will be just the square of our wave function. So you have square root of 3 over b, capital A over A, x over A. So our normalization constant is just so this will be the absolute value of square root of 3 over b, our normalization constant, and then x over A squared dx. So 3 over a b, integral from 0 to a of x squared dx. So this is just a simple integral, and this will give you a probability of a over b. So that's the probability of finding the particle to the left of a. It's a over b. So the probability or the area under the curve here is a over b. And of course, if you are asked to find what's the probability of finding the particle to the left of, to the right of A, so that is this region. So you can use this formula where your limits now will be from A to B, or since you already know the probability from to the left of A, so you just need to subtract A over B from 1 to get the probability to the left of A as 1 minus A over B. So if you add these two probabilities, it's equal to 1. So there are only two sides of our distribution here, to the left of A and to the right of A. So let's now check the limiting cases. B is equal to A. If B is equal to A, then that means that the probability is, so B is just A over A, so the probability is 1. So in terms of the sketch, if B is equal to A, so if point B actually coincides with point A, then your probability distribution will look like this. So the only area under the curve is to the left of A or to the left of B, and that is the total probability, which is just equal to 100%. There's a 100% chance that you will see the particle to the left of A. 0% chance that you will see the particle to the right of A, because there's no area under the curve here. There's no probability. For the second limiting case, B is equal to 2A. So if B is equal to 2A, then you have A over 2A, so 1/2. So in terms of the sketch, you will notice that the sketch will now look like this. It will now become symmetric. Unlike in the our original sketch, it's not symmetric. But here it's now symmetric. So the probability here is 1/2 to the probability of finding the particle to the left of A is 1/2. And also, if you want to get the probability of finding the particle to the right of A, it's also equal to 1/2 due to symmetry. Okay, last problem. What is the expectation value of our position x, or our variable x? Sorry. So to find the expectation value, we use this formula. So you just plug in our values. So we plug in our values here, the absolute value of psi squared multiplied by x. So therefore we will get, so you square your wave function, so we square our wave function and then evaluate from negative infinity to positive infinity. And actually, sorry, I forgot to mention the x here, because we are finding the expectation value of x. So again, the only interval from negative infinity to positive infinity that will have value will be from 0 to A and from A to B. So this will be equivalent to two integrals. So you have from 0 to A, so x, absolute value of your psi squared dx, plus from A to B. So we have two types of wave function, or two expressions for the wave function. So this wave function expression is different from this wave function expression. This is from 0 to A. So from 0 to A, you have the normalization constant squared. So if you square root of 3 over b, so you will get a factor of 3 over b. So integral from 0 to A of x, and then your wave function from 0 to A, if I'm not mistaken, is x over A. So you square that, you will have x squared over A squared. So this will now become x cubed over A squared. So I will just put the A here, the constants, dx. And for letter B, from A to B, so you still have 3 over b, the factor, and then you will have the b minus a squared factor, and the inside the integral will be b minus x squared dx from A to B. Okay. So this is just an elementary, these are just elementary integrals, and I will leave the rest of the solution to you. So you just expand this into 3 terms, so this becomes 3 integrals. So all in all, you have 4 elementary integrals, and you will get this value here. So 2a plus b over 4. So this is the mean or average value, 2a plus b over 4. So if, for instance, we take the limiting cases, when a, or when b is equal to a, what happens to your expectation value when b is equal to a. So if b is equal to a, you will have 2a plus a, so you have 3a over 4. So your expectation value is at 3/4 a. 3/4 a, so before a, 3/4 the distance. So if this is from 0 to a, your expectation value is somewhere here, 3/4 a. So if b is equal to 2a, what will happen to your expectation value in this limiting case? So you will have 2a plus 2a, so you have 4a plus 4, so you will have x is equal to a. So in the limiting case, b is equal to 2a, then your expectation value is that x is equal to a, which is, if you will recall, in our plot, this is the limiting case b is equal to l. So the expectation value here, or the average value, is at 3/4 a. But for the second limiting case, for b is equal to 2a, this one, so the expectation value is at x is equal to a. So it's at the middle of the distribution. So this one. Okay. So I actually have another example here, but this example actually resembles the previous example in the example in the previous lesson, where we have a probability density rho, and the solutions actually to this problem are just similar, or actually in some cases exactly the same. So you are given this wave function. You will notice that this wave function now has a imaginary part, negative I omega t, where a, lambda, and omega are positive real constants. So you need to take into account this term here if you are getting the absolute value of psi squared. So you take the conjugate, multiply by itself. So these are the questions. So first, you are asked to normalize your wave function. So of course, you use the normalization condition. So given this value of your wave function or expression, what will absolute value of psi squared look like? So now you have a complex wave function, which is the wave function in general. So your absolute value of psi squared here will just be the conjugate times itself. So in this case, the conjugate of this wave function will be a e to the negative lambda absolute value of x. The conjugate of e to the negative I omega t is e to the positive I omega t multiplied by psi itself. So a e to the negative lambda absolute value of x e to the negative I omega t. Okay. So you will get a squared e to the negative lambda absolute value of x. So you have negative 2 lambda absolute value of x. And then you have e to the I omega t, e to the negative I omega t. So you add their powers and it will just be equal to e to the 0 or 1. So in this case, our absolute value of psi squared is time independent. There's no more time component. So t here is time. There's no more time component here. It becomes independent of time. And this is just equivalent to our actually probability density that we have before. But in our probability density that we have before, in the previous lesson, it's just a here. But here in our current probability density, it's a squared. So the equations are the same, the formulas that you will use are the same, but in this case, your a, instead of equal to lambda, you get square root of lambda. But the expectation values are exactly the same. 0, ang expectation value sa x. The expectation value of x squared is exactly the same, 1 over 2 lambda squared. And the standard deviation is 1 over square root of 2 lambda. The sketch is exactly the same. But instead of rho here, we now have absolute value of psi squared. And then in the previous example, you were asked to find the probability of finding the particle within standard deviation. But here, you are asked to find the probability that the particle can be outside. So in the previous example, you find the probability inside the within standard deviation. But now, outside the range, negative sigma to positive sigma. So this, you need to solve for this area here, area under the curve here, plus area under the curve there. And in the previous example, you get 75.7%. And in this example, just subtract 75.7 from 100%, and you will get 24.3%. So exactly the same manner of solving this problem. So that ends our lesson for this session. For our next lesson, we will be discussing about the operator form of the quantum momentum. So we'll discuss quantum momentum, and in doing so, we'll also generalize the concept of expectation values. So that's it for today. I will see you again in our next session. Goodbye.